All right, so let's start chapter 17. Chapter 17, as you can see, is confidence intervals for means. And like with chapter 16, I said, anytime you see the word proportion, we are talking about a uh, categorical variable. Well, in the same way, whenever you see the word mean, this context, we are talking about a quantitative variable. And so again, you need to be able to easily identify if the variable we are looking at is categorical or quantitative, because as you'll see, the idea is the same, but the main difference is we use different symbols for quantitative variables than we do for categorical. And so there are other differences that we'll talk about, but that's the main one. So you need to know when you see variables, what they're representing and what type of variable they go with. So we'll start with the central limit theorem. And the central limit theorem says that the sampling distribution of any mean becomes nearly normal as the sample size grows. And so it doesn't matter what the population data looks like. If you're taking samples, and this goes back to what we talked about in chapter 16, where you take many samples and you get, in this case, the mean of the sample, and then you plot those sample means on histogram, then as the sample size increases, or the bigger the sample is that you are taking over and over again, the closer that sampling distribution will be to normal. And so what are the requirements? Independent randomly collected sample, and that's all. Now, if you remember from chapter 16, we had a third requirement, or a fourth, depending on how you want to count them, where we had a success failure condition to be met. And we don't need that here, because with quantitative variables, we don't have success and failure. That really only applies with categorical variable, because either you're in that category that you're looking for, or you're not, or the thing is not in the category that you're looking for. It's in either or. With a mean, you're typically measuring something. So it could be cost, it could be height, it could be weight, it could be temperature, any of these things. And we don't really have a success failure, unless you want to divide it up and say we're above this or below this. But generally speaking, with quantitative variables, we don't have success failure. We're just measuring things and putting them on the histogram. So the sampling distribution of the means is close to normal if either we have a large sample size, or just the population in general is close to normal. So if we have something that is a normal distribution, like say the weight of some animal, the population would be normal. So if you're taking samples, then clearly that's going to be normal, whether your samples are large or small. But as we'll see in a second, the large sample size also helps with that. So here's an example and this is a simulation. So there are websites that you can go to that will show you how this works. But basically, if we have a population, we have population data here, CEO compensation in thousands of dollars. So 5,000 here, that would be $5 million. And we can see most of the CEOs are in this range, whatever that range is, and we're skewed to the right, heavily skewed, so not symmetric at all. But if we take many samples of a sample size of 10, you can see it's getting less skewed. So these are individuals, and these are samples. So like we talked about in chapter 16, where we looked at the histogram of the sampling distribution, these are not representing individuals. These are representing samples. And the sample sizes are 10. And so we can see we're getting a little bit less skewed. And we can see here, we're getting a little bit less skewed when we go up to 50, and then it went in as 100, went in as 200. Now when we get to 200, we're pretty close to normal. And so that's all that means. The larger the sample size is, the closer you get to normal. And then again, there are websites that can do a simulation of this. You can kind of play with the distribution, what it looks like. You can change the sample size. um, and then see how that works. But kind of intuitively, if you think about this, it does make sense because if you let's just take height, for example, and let's just take men's height. So if you randomly pick two men and I randomly pick two men, and then all of us randomly pick two men, it's not unlikely that several of us could get two very tall men, and then our sample average of the two men that we picked would be, say, 6'5". That is not out of the range of possibility. Or on the other end, we could get two men, and the average height would be 5'5". But if you're going to pick, say, 50 men, it's not likely that your average height is going to be an extreme value like 6'5", because as you pick more and more, you're going to get more and more of the men in this case who are close to the average height. So that's also why, like we'll talk about, and we did talk about this in the last chapter too, when the sample size increases, the variation or the standard deviation decreases. And we can see this here too. So presumably we're around zero here. The range is from 0 to almost 40,000. Here, the range is from 5,000 to 18,000. Here, the range is from 6,000 to 14,000, then 8,000 to 12,000. So we're getting much, much closer in our range of values. And that's because the sample size is increasing, and you're not going to have all those, you're not going to have these samples like if you pick the two men where they're both well over 6 feet tall and it's well above average. You're going to get a lot more towards the average here. All right, so let's move on to the next page. And so when a random sample is drawn from any population with a mean mu and standard deviation sigma, its sample mean is y bar. And we can use, so sometimes you'll see y bar, and you could also see x bar. The letter is not the important part. The bar over the letter variable tells us we're talking about a sample mean. But the sample mean x bar is a sampling distribution with the same mean mu, and all that means is if you make a histogram of your sample means, the middle of that distribution will be the population mean mu. So, and going back to variables and what they mean, so mu means population mean. And we did talk about this back in chapter 10 when we were doing sampling methods. And we said that typically Greek letters are talking about parameters or population numbers, and English letters are typically talking about sample numbers. And the case holds here. Mu is the population mean, x bar is the sample mean. The standard deviation of the sample means is sigma over square root of n. And we write standard deviation of the sample means, or standard deviation of y bar, sigma over the square root of n. And sigma is just the population standard deviation. So again, you need to make sure that you understand the difference and can recognize the difference between mu and x bar. One is on the population, one is looking at the sample. Sigma, Greek letter, is the population standard deviation. So no matter what population the random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough. So we kind of talked about that. The larger the sample used, the more closely the normal model approximates this distribution. So we talked about all this. All right, so confidence interval for the mean. And let's relate this back. So again, mean means that we're talking about a quantitative variable. We talked about confidence intervals for proportions, which are for categorical variables. And if you remember, draw a number line, we take a sample, we get a sample proportion, we put p hat there, and then we go out some distance and we can find a confidence interval for where we believe that p likely is. Here, we're looking at quantitative variables, and so we take a sample and we get the sample mean, And so that is X bar. And so now instead of P hat, which is the sample proportion, we're going to put X bar in the middle, which is the sample mean. And we're going to go out some distance. And again, we call that distance the margin of error. And so now we're trying to estimate where mu is, or the population mean. So we're given or find the sample mean for some sample that we want, and we're trying to estimate where we think the population mean is. Now, the problem is we don't know sigma. So kind of like when we were doing this with the proportions and we didn't know what P is, so we couldn't find the standard deviation of P hat because that is square root of PQ over N. We had to estimate it using P hat. Same thing here. We're going to estimate standard deviation with standard error. Standard error of Y bar is S over square root N, and S is just representing the sample standard deviation. All right. So it's kind of, if you pay attention and notice the patterns, notice the similarities between this chapter and what we were doing in the last chapter. We're doing exactly the same thing. It's just we're talking about different variables. And especially with the standard deviation of a quantitative versus a categorical, we're calculating it differently. So that's why we have these different formulas. So practical sampling distribution model, when certain assumptions and conditions are met, we talked about that earlier, the standardized sample mean is given by this formula here. So T equals Y bar minus mu over standard error of Y bar. Now, if you remember from chapter 5, this should look familiar. It should look something like the z-score. So you remember the z-score was z equals x minus mu over sigma. And so the x was the data point, and here y bar is a data point on that histogram. It is the sample mean, but it's still a data point. So it still follows that formula, mu and mu, sigma, which was the population standard deviation, and this is the standard deviation of these sample means that we're getting. So this is what's called a student's T model with n minus 1 degrees of freedom. And we won't spend too much time on degrees of freedom. We'll mention it here in a minute. Estimate standard error, again, with this S over square root n. So degrees of freedom. So this is very similar to the normal model that we've done plenty of times. With the normal model, we have two parameters that we need to know in order to discuss a normal model or to find different probabilities and that kind of thing. So we need to know a mean and we need to know a standard deviation. Well, with a t distribution, we need to know the mean and the standard deviation, but we also need to know the degrees of freedom. So just changing the degrees of freedom, and degrees of freedom is just n minus 1. Changing the degrees of freedom changes this model, just like with the normal distribution, changing the standard deviation changes the normal model. So same thing. So when the assumptions are met, the confidence interval. Now, if you remember, we said this generally speaking in the last chapter, no matter what the parameter is, your estimate or your sample number, sample proportion, sample mean, whatever it is. And we're going to go plus or minus the margin of error. So we talked about that last time. Just generally speaking, that is what a confidence interval is doing. You get sample, whatever measurement of that sample you're looking at, that's the middle of your interval, and then you go out some distance, and that's your margin of error, and there's your confidence interval. So when the assumptions are met, the confidence interval for the mean is X bar, and it makes sense. We're using X bar. In the last chapter, we used P hat, plus or minus. Now, in the last chapter, we used Z star. Now we are using T star, and T depends on n minus 1, the degrees of freedom, times the standard error of Y bar. And so if we, well, I guess we should use X again. I'm used to using X. But either way, X bar or Y bar, it doesn't matter. So now if we compare this with the confidence interval that we did in the last chapter, in the last chapter we had p hat plus or minus z star times standard error of p hat. So it's the same idea. It's just, again, with quantitative variables, we have to alter things slightly. And so it looks a little bit different, but we're still doing the same thing. So the critical value T star depends on the confidence level C and the degrees of freedom n minus one. All right, so I think we'll stop this video here and we'll pick up an example on the next one.